Hi, today I'll be talking about our work on learning to communicate and correct pose errors. Learned communication makes multi-agent systems more effective by leveraging distributed information and computation. However, relying on distributed information makes individual agents susceptible to erroneous messages. In self-driving specifically, while localization systems have become quite accurate, they are still susceptible to errors. Past multi-agent self-driving systems show limited tolerance to this implicitly, but none take steps to solve this issue. We address pose noise directly. In our work, we study V2VNet, a state-of-the-art vehicle-to-vehicle communication network for joint object detection and motion forecasting. We illustrate V2VNet in a simplified case where the ego self-driving vehicle, in red, receives a message from another self-driving vehicle, in blue. Both vehicles take LiDAR data as input and process it using a convolutional neural network to produce a spatial feature map called a message. The ego car receives the message and warps it to match its own perspective. The message gives the ego car significant visibility into the scene, particularly against occlusions. The warped incoming messages are aggregated using a graph neural network, then processed by a convolutional header to produce object detection and motion forecasting outputs. When inevitably there's pose noise, messages are poorly aligned, producing unusable features. This leads to downstream performance that is worse than if the agent had not received the message at all. Our contribution is an end-to-end learned neural reasoning framework. This system corrects the incoming messages before they are aggregated. We will focus on the ego car, in red. First, we use a pose regression module. For each incoming message, the convolutional neural network takes the ego message and a warped incoming message concatenated and outputs the correction for the relative pose error, which has two translational components and one rotational component. Intuitively, after correcting the relative poses, each vehicle has its own distinct estimate of where all the other vehicles are. The consistency module allows vehicles to communicate the corrections to reach a consensus about each other's pose. Our synchronization algorithm uses a conditional Markov random field where each vehicle's pose is a node and we condition on the predicted relative poses. After the vehicles reach a consensus about the poses, there may still be outliers poisoning the messages. We use a CNN which takes the ego message and the corrected warped other message to predict an attention weight. This weight is used to attenuate outlier corrected warped messages during aggregation. Finally, the aggregated messages are used downstream to perform detection and forecasting. The whole system is learned end-to-end with a combined detection, forecasting, and attention loss detailed in the paper. We are primarily interested in the detection and forecasting performance of our model under pose noise. Here, we show the average precision across various levels of pose noise. In the x-axis, the first number is the standard deviation of the positional error, while the second is the standard deviation of the rotational error. Our first baseline is a solo vehicle that receives no messages, which has constant performance because it isn't affected by erroneous messages. Next, we show V2VNet, which shows strong performance at no noise, but quickly deteriorates with noise. Training with data augmentation of 0.4 meters and 4 degree standard deviation improves robustness significantly. Our method, trained with the same data augmentation, shows nearly constant performance across noise levels. We also compare learn to sync, a state-of-the-art synchronization algorithm used in place of our consistency module. We can also see our model generalizes and is robust against noise much higher than seen during training. We observe a similar story for motion forecasting, where we measure the L2 error of the prediction 3 seconds into the future. Here is a qualitative example of our framework in action. Without the corrections, the detections and predictions of vehicles farther away from the ego car are shifted, whereas with the corrections, the detections are correct. Here is another qualitative example where we can see the same phenomena of shifting far away from the ego car, but correct alignment with the correction. More examples and experiments can be found in our paper. To conclude, collaborative self-driving will bring the safety of self-driving to the next level. In order to be safe in realistic conditions, we must be robust to noise. We propose and empirically show the effectiveness of an end-to-end learned neural reasoning framework, where agents estimate errors, reach a consensus about these errors, and suppress remaining outliers. In the future, we aim to extend our framework to reuse computation more efficiently and to correct more general types of noise. Thank you for listening.